Hello, welcome to this tutorial where we will be modeling an integral bridge of composite steel type. The bridge is a single span bridge with 4 steel girders and a composite deck which has abutments on either ends supported on top of piles. In this particular example we will be doing static analysis, live load optimization, soil structure interaction, and we'll also simulate the construction stage analysis of the integral bridge, which will include the composite action, and then we'll see the results and see how we can extract automated design calculations as per Eurocode for the composite steel bridge, as well as for the reinforced concrete piles. We'll do the member check and we'll see the reports. Okay, so this is the blank MIDAS civil file. I'll start with general finite element modeling for the integral bridge. So let me just create a node which is just an origin point. Apply. A node is created here, close, and then I'll extrude this node to create the main girders. So I'll be making a grill edge model for the integral bridge. So I just selected the node, just keep material and section as 1 1. I'll be assigning materials later on. So just enter here 5 meter 8 times, so the span of the bridge is 40 meters. I am meshing or dividing the girders into 8 segments or 8 elements. Just click apply. Okay, so I have a 40 meter girder. Now I'll just copy this girder to the Y direction. So I select everything here and go to translate elements, copy in the Y direction. The center to center distance between the girder is 3.5 meters, so I just enter 3.5 here and copy 3 times 3 girders and click apply. Okay, so I've got my 4 girders here. Now I'll create cross beams or cross bracings, which will be channel type sections. So just close this, go to create. Okay, just click these 2 points and I'll just copy this particular cross beam to these locations. So I go to translate. Now I'll measure the distance for the copy by just clicking on this box, clicking on these 2 points to measure the distance and specify how many times I need to copy. So 8 and apply. Okay, so I've got the cross girders all copied here. Okay, and now I'll model the abutment. So for the abutment I'll use these reference lines to create shell elements or wall elements vertically. So I just use the extrude option again, line to plate, and this time in the vertical direction. Say my abutment is a 5 meter deep abutment, so I say -1 5 times, that is I am dividing it at 5 intervals, something like this. So I've got the abutment here. Now I'll create some piles from these base nodes. So again, change to the front view, select the bottommost nodes and select this to node to line, and just specify here in the Z direction, say it's a 15 meter, the pile lengths are 15 meters, so 15 meter, 15 times minus 1 meters, minus because it's in the vertically downward direction, and click apply. Okay, so the geometry is now being complete on one side for the abutment and piles. I'll use the same boundary conditions and same loading conditions on the other side, so I'm just keeping it for later on when I'll be copying the entire abutment and piles to this side of the bridge. So right now what I will do is I'll start by assigning some materials and sections to this geometry. So I go to properties, materials, and I start defining some materials. So first material is steel, which is, I just select type of design steel, select S355 grade, which I will be using for my plate girders, apply, and same for concrete. So for concrete I'll select for the slabs C35, click apply. For the design purpose of the composite steel girder, I will select a steel reinforced concrete material, so I'll again select 355 and 35. For this is just for the design purpose. For analysis, the software considers the materials during the time dependent during the construction stage analysis. And then there is one more material property. This one's for the transverse beams for the grillage members. So the deck will be modeled as a grillage of longitudinal and transverse elements. The transverse elements, I will provide them with the modulus of elasticity similar to concrete, but their weight density will be 0. So I'll just select C35, make it none, so that I can edit these entries. So I keep weight density as 0 and specify the name as a cross beam. Okay, and click OK. I'll just change the name of this material, make it SRC, so that I can identify it later. Okay, now I'll go on to define some sections. So section properties, add, and start by defining first the composite girder sections. So composite steel I, which is plate girder. Here I need to define the effective width of the girder, so it's 3.5 meters. Number of steel girder is 1 per slab, and width of the slab, thickness of the slab, which is 250 mm. Then height of the web for the I girder, so that's 1 meter. Width of the flange 500 mm or 0.5 meters. Thickness of the top flange, which is 50 mm or 0.05 meters. TW for thickness of the web, that is 0.02 meters or 20 mm. And bottom flange will keep it same as the top flange, so 0.5 meter and 0.05. Now we will select the materials for composite action. So for the concrete it's 335, for steel it's 355. Click OK. You can see the modular ratios have been automatically calculated. Now in our analysis we will keep the reference line of each main girder as the top of the slab, so we will change the offset of this section to center top. Click OK. So now the reference line is the top fiber of slab. name of this girder, so I'll just name it as mid span, because I will use two different types of sections for the main girders, because I want a non-prismatic or tapered section between my abutment and up to 15% of the span. So I'll just use separate sections for mid span and separate section, a tapered section for the abutments. Okay, if you want to see the calculation results, you can just click here and see what's the value of the stiffness before composite and after composite. Okay, click apply, and you can see as soon as you hit apply, all your sections or elements have been assigned with the first section ID 1 by default. We can change it later on. So right now I'll just create a section for the abutment, near the abutment. So near abutment, only the height will change here, so 1.4 meters, and click apply. Then I'll go to user defined section or database section. I will select a cross beam section now. So the cross beam will be a channel section. So we'll define a channel section, select channel, type in cross bracing, and user defined type. Height is 500 mm or 0.5 meters. Flange width 100 mm, 0.1 meters. 0.01 meter is the thickness of the flange and also the thickness of the web. And the offset for this section will be shifted from the extreme fiber, shifted 0.7 meters down. So click OK, and click apply. Then we'll define a section for the piles. So pile, and select a solid round section, and a diameter of 1 meter, and this is center. Click OK. No offset for the piles. Click apply. And finally a section for the transverse grillage members for the deck. So for the deck, specify a rectangular section. Section shape is not important if you select the value type section, because the purpose of value type section is to be able to edit the section properties. Since for the dummy transverse members, or rather I should say dummy transverse members, I can type in the height or depth of the slab, 0.25 meters, and say the width is somewhere 1.6 meters. This is the transverse section dimension. Calculate section properties. Now it does calculate the section property for this shape, but we can change these properties. So if we have any different shear area in the transverse direction, we can manually edit these values. I can choose to ignore the shape for the analysis, so I can keep it 0, 0 if I think that the shape of the transverse grillage member is not very important for the analysis. We just want a transfer of forces in the transverse direction, so that we can have we can see the distribution of forces in the transverse directions as well for the deck. So I'll just keep it as 0, 0. Not interested in the shape of the section, the transverse sections, just interested in the properties. That's it. I'll click OK, and then I'll define a thickness for the abutment. So thickness, and the abutments are 1.2 meters thick, so 1.2 meters. Click OK and close. As soon as you enter the thickness, you can see the thickness here. Now in the works tree, which is here, you can see that there are some information listed here. Nodes, you can double click to select or highlight them. The number of the nodes will be displayed here, so whatever you select, the corresponding number of that element or that node will be displayed in these two boxes. This is the node selection box, this is the element selection box. Plate elements, materials, by default everything is assigned with steel material. We have to change it, so I'll just switch off the fleshed view. You can switch off the fleshed view from pressing this small hidden option here. So click here, switch off the fleshed view, only line view is visible. So now I will start assigning some properties. So steel, these cross bracings, they are steel, so I'll just select them. So select by creating a window, so from right to left. Okay, drag and drop steel. Okay, select previous by clicking here, and this time drag and drop cross bracing. Okay, you can check the shape. Okay, okay, so the cross bracings have been shifted 0.7 meters upwards. We would like to shift it with reference to the centroid, so I'll just change it to centroid by right clicking on cross bracing. Click OK. Okay, now they are in position. So you have to adjust the offset as per the alignment you want them to be. Okay. Okay, now cross bracings are specified. I have intentionally left this last girder unspecified because I will not be using it for the analysis, so I'll just delete it. So select all of them and press delete. Okay, now I need to create some transverse grillage members, so I will divide my main girder. So I just select the main girder this way. Okay, and just go to node elements, divide, and I'll divide it into three parts, and apply. Okay, so the main girder has been divided into several parts, and I will now create my cross brace or the transverse beams. So cross beam material is selected and dummy transverse members are selected. This will represent the transverse behavior of the deck. Click on nodal connectivity and just draw the elements like this. Okay, I can choose to use the extrude option as well to just extrude them, or I can copy these newly created elements. I can just click translate and click on these 2 points. Okay, and say translate 8 times. Apply. Translated these two more than once, so just click delete. So that's it, the cross beams are now copied. You can double click to check. So if I double click here, double click on the dummy transverse beams, I can see that these are the transverse grillage members for the deck. and similarly if I double click here, the sections corresponding to cross beam or dummy beams get selected. Okay, now I'll change the pile sections. So just select by creating a window either from left to right or right to left, just to select all the pile elements and drag and drop pile. Okay, select previous and drag and drop C35, so that's the strength of the pile that we will be using. Now select the abutment elements, select by clicking like this and drag and drop. So abutment is also concrete 35 grade. Okay, we can check this view. Okay, so still we don't have the abutment and piles on the other side because I will copy all of them together. Now we need a tapered section here and also here, so we will generate a tapered section. So we again go back to properties, section properties, add tapered, and the type of the tapered section is composite steel I. So just select steel I, name as the section from left to right, left to right, again number of girders 1, slab dimensions 3.5, 0.25, sorry 0.25, and now I'll import the first section, which is near abutment. Import, scroll down, go to the second import, import the second section, which is midspan. Import. So this specifies the two sections at two ends for the taper. Select the material C35 S355, click OK. Change the offset, so the top will be the top of the slab will be the reference line. Click OK and apply. Now we will create another one from right to left, so right to left. This time scroll up, import midspan first and then scroll down, second import near abutment. Import and click OK. So that's the two sections, tapered sections at two ends we have defined, and now we will only activate the main girders. So I'll double click on midspan and press activate. Okay, so I have only the main girders in view. Now select these nodes, the first 5 elements from the left, and drag and drop left to right. Okay, select 5 elements from the right, drag and drop right to left. Okay, now since these are all staggered or discrete, we want a smooth taper, so we will group them under the tapered group option. So tapered group name is left to right, and the elements which are included in this group, we will select them by creating a window like this. Enter a polynomial function, say parabolic type of taper, and add. So you will see the parabola is in this direction, a concave type of parabola. We will reverse it, so we just change the origin point to J, modify. That's reversed now. Now do the same thing for the right side, so select the right side and just change the name. So just unselect all and select the right side, change the name to right to left, keep this as 2, keep the symmetric plane from I, and add. Okay. Close this. So now we have the exact section taper and section properties for the main girders. We will activate all the elements, so click on activate all. That's all of them activated. Okay, now comes the situation where we define the boundaries. So we go to boundary, and for our integral bridge we will define springs for the piles, and we will apply some soil pressure for the abutment. So the springs that we define for the piles will be non-linear springs as well as linear springs. So to define a support or a spring, we go to integral bridge option, click on integral bridge. Okay. Select the pile spring option, select all the pile nodes, select the soil type, say soft clay, select the ground level, say this is the ground level here, pile diameter is 1 meters, unit weight of soil from the geotechnical study you can enter, then subgrade reaction from the geotechnical study you can enter some value, say 10,000, and apply. So the software has automatically created springs for all the piles, soil springs. You can see the properties in the works tree. Right click here, properties, it will show you the stiffness considered for the springs. Okay. Now we will apply some loading on the bridge. So for the loadings, we go to load and create some load case names. So static loads, static load cases. First load case is self weight. So it's a dead load type, so dead load, add. Now wet concrete load, we will not apply the weight of the concrete automatically, rather we will apply the weight of the concrete before the composite action has taken place. So it will be applied as a wet concrete load on the steel only. So wet concrete load, add, and some other loads such as parapet load, again a dead load, add, temperature load, pressure, change the type to temperature, T, add, earth pressure, change it to earth pressure type. Okay. So these are some of the loads that we will be applying on the bridge, plus the live loads. So we'll start by applying some self weight. Now before applying the loads, I'll create some groups for identifying or selection purpose. Groups are very useful when you want to select a particular elements. You can just include them in a group and always keep on selecting the group instead of selecting individual elements. So in the group tab, I'll go to structure group and right click to get new. Say this is the abutment and piles. Okay, I'll switch off the hidden view and you can select all the abutment and piles under this group. So after selecting, just drag and drop. Now create another one, right click new, and this time add main girders. Select all the main girders in this group. So I'll just right click and activate the second tree menu. Right click tree menu 2, works. Double click on midspan and also right click on left to right, select plus, and right to left, select plus, and drag and drop main girders. Then right click new, this time for the cross bracings, which are steel girders. Double click cross bracings and drag and drop. Right click structure group, these are the transverse grill edge elements. Transverse elements. Okay. Double click dummy transverse, right click transverse elements, and we'll create a boundary group for all our soil springs. So we'll name it supports. And also right click on load group, new, create a load group for self weight. Right click new, create a load group for wet concrete. Right click new, create a load group for the parapet loads. Right click new, create a load group for earth pressure. So few load groups we have created. Now we will start assigning some loads. So I go back to works, and now we'll start by assigning some loads on the bridge. So self weight, select load case name as self weight and load group name as self weight again, and we'll assign -1 in the Z direction, that is the gravity direction. Add and close this. Then we will apply some wet concrete load on the main girders. So now we'll select using the main girder group that we created. So group main girder, double click, selected, and go to loads, element loads, wet concrete group, and apply in the global Z or vertical direction the units kilonewton per meter. And we can also write down a function to calculate the wet concrete loads. So I'll just use a simple multiplication function to calculate the effective wet concrete load on each main girder. So 3.5 width of the slab, effective width, depth of the slab into material density, which is 25 for concrete, and just click apply. So concrete dead weight is applied on the steel girders, and then we will apply some parapet loads on the end girders. So just double click on the, change it to the side view, and select only the edge nodes by creating a window, the exterior girders get selected. Change this load case to parapet load, parapet, and type in the value of the parapet load, say minus 20 kilonewton per meter, and apply. So this load has been applied on the edge girders, and now we will apply loads on the abutment as earth pressure load. So hydrostatic pressure load is selected. Select load case name as earth pressure, and I'll change the direction like this. To select the abutments, just change to the works tree, double click on the plates, all the abutments get selected. Select the reference level for the hydrostatic pressure load, so click here and click on the topmost point. Select the load at the top, which is say 2, and enter the load at the bottom of the abutment, the gradient for the load, so it's 10. So every meter the load will increase by 10 kilonewton per meter square on the abutment face, and click apply. So that's the soil pressure applied on the abutment. Now close this. Okay, now I'll copy this entire system of abutment and piles to the right side. So just change it, just select by window, change to isometric view, and we'll use the translate function. So node element, translate, and translate by clicking on this box. Click on the first point here and the last point here, and click on intersect node element, and also we'll copy all the attributes associated with the nodes and elements, that is supports and boundaries and loads, and click apply. The earth pressure load has also been copied, but if you see here, the earth pressure is reversed here, so we need to reverse the local axis of the abutment. So select the abutments by clicking on selection tool, select this abutment and go to node element, change parameters, reverse element local, planar type, reverse element attribute, and apply. That's reverse now, which is correct. Okay, now we have to include these new abutments also in one group. So just create a window like this and drag and drop abutment and piles. Select all of them and drag and drop abutment and piles, so all the abutments and piles are associated in one group. Also the supports should be associated under the support group, so just select all the abutment and piles and drag and drop supports, so everything every support will come under the support group. Click OK. Go back to works. I'll just close this tree menu. Now we will apply some temperature loads. So for the temperature loads, what we can do is select the group and select only the main girders. Go to loads, temperature loads, element temperature. Okay, the temperature units, if you see, we have to select temperature here, and the temperature units is in Fahrenheit, which can be changed from tools, unit system, Celsius. Click OK, and you can change the final temperature of the bridge. We can also assign an initial temperature, so just click on this box and select initial temperature, enter as 15 degrees, click OK, enter final temperature as 30 degrees and click apply. So temperature load is applied on the bridge on the main girders. Now after this procedure we will start creating construction stages. So our first construction stage we will create by going to load, construction stage, define CS, add. So in the first stage, which is stage 1, the duration is, say, duration of 15 days. The first stage will have all the abutment and piles, add. It will have all the supports, add, and it will have loads, that is self weight, as well as earth pressure load acting on the first day. Click apply, and cancel this. Click add, stage 2. This is a stage where only the main girders will be activated. So the duration is again 15 days. Activate main girders with cross bracings. So steel, only the steel will be activated. Go to boundaries, supports are already there, no new supports added, so no need for activation. Loads, self weight is already applied on the bridge. In this stage we will apply the wet concrete load on the last day. So last wet concrete load, we'll save the additional steps, so both the first and last step results will be displayed. Just to note here, first day there is no load applied. The load is applied on the last day, that is 15th day of this stage. Click OK. Stage 3, this is the stage when the concrete is actually casted and the composite action is complete. So we can say this is the stage for, say, again 15 days, and this time transverse grillage members will be activated because the slab has been casted and will have a grillage behavior in this stage. Loads, no new loads added. The weight of the slab has already been considered in the previous stage, so it will keep as it is, and click OK. And then the last stage, stage 4, this is a long-term stage, so say 100 days, and with all the elements already activated, boundaries activated, load. This time we activate the parapet loads. So add and click OK. Close this. Now we will also define at which stage the composite action has to be completed. Now if you remember, we need to define the slab weight as 0 because we have considered the slab weight as UDL or element beam loads on the main girder itself, on the steel itself. So we will use a zero density material for the slab. We had already created a zero density material with same modulus of elasticity as the slab, which is known as the cross beam material. So we'll go to loads, construction stage, and composite section for construction stage, where we define that when the composite action of the bridge of the main girders will take place. So add here and add the stage where the steel girders are activated for the first time, so that's stage 2. Select the section, that's midspan, change material. So part 1, which is steel, which is part 1 here, The material is S355. Stage of activation is stage 2. Age is not necessary because we are not doing any time dependent analysis here. For the concrete, which is part 2, define material, define cross beam material because this is a zero density material for concrete, and the stage of activation of concrete is stage 3. That is, at stage 3 composite action will be completed. Apply. Do the same for left to right section. So left to right is a taper type of section. Do the same thing, materials S355 for first stage, or the steel material for part 2 is cross beam 3. Apply. From right to left, material is 355 stage 2, material cross beam stage 3, and click OK. So the composite action has also been defined in the bridge. Now we will browse through different stages to check whether we have assigned the information correctly or not for the stages. So we'll browse through stages. So first stage, only abutment and piles. You can see that boundaries are also activated here. So just to be more clear, I'll define the display the boundaries. So you can display any boundary and load from the display tab here. Loads, select all of them, and just I'll check off values. Apply. And boundaries, select all of them, apply. Okay, so browsing through stages, stage 2, steel only with also wet concrete load. You can see here display wet concrete is there. Stage 3, that is the slab has been casted. You can see the hidden slab. And then stage 4, which is also consisting of the parapet loads over here. So all the loads have been all the stages have been built up. Now we defined by modeling the live loads on the bridge. So for the live load distribution, we select a group consisting of all the cross beams. So right click on structure group, new, this is cross beam group, and we can select all the cross beams here. So first I will activate the deck, activated. Now I will select all the cross beams like this and drag and drop cross beam. So all the cross beams are transverse elements including steel cross bracings as well as concrete grillage members. They are included under cross beam group. Now I'll start by defining the live loads. So I'll check off the load display. So loads, click apply, cancel. So load, moving load, we'll use the Eurocode live load analysis in this case. Eurocode, traffic line lanes should be defined first. So all the notional lanes has to be defined with respect to a reference line. So we will use this extreme line here for defining all our lanes or carriageways. So traffic line lanes, add, this is lane 1, eccentricity is minus 1.5, and cross distribution is cross beam type, that is load will be distributed via cross beam. So select cross beam and select the group that we just created, and select on the first point and the last point here and click apply. So first lane is generated. Delete all this information here, delete, enter lane 2 and change it to -4.5 and again click on first point and the last point on this line and click apply. Lane 2 generated. Change this to lane 3 and to -7.5. delete all the previous information, delete here and click on the first and the last point, click apply. Lane 3 is generated. And finally a remaining area, our A lane, this is -10 and let me just keep it -9.5. remaining area lane width, I'll keep it as 2 meters and delete everything here, click OK. So remaining area lane has also been generated. Now we'll define some vehicles to run on these lanes. So define vehicle and add standard, road bridge, load model 1, define some adjustment factors, so 0.61 for example, 2.2, 2.2 and keep 1 for the remaining area. Psi factors can be entered as per the national annex, click apply and we'll repeat the same for load model 3. So load model 3 we can use the recommended Eurocode ones or the UK national annex load model 3, say SV196 and click OK and close this. Go to moving load cases, add the first load case is load model 1 only, define load model 1 and footway. We haven't defined any footway, so we'll just leave it none. Now depending upon the frequent and characteristic load combination, we can either choose to ignore psi factor or keep it as it is. So select all the lanes, bring them to the selected lanes category, select remaining area, bring it to remaining area category and apply. Then we'll model the second load case, load model 1 plus load model 3. This load model 3 vehicle can also straddle between lanes, so we'll use multi-straddling. Ignore psi factor. Load model 3, we can select between which lanes it is supposed to straddle, so we can select lane 1 lane 2 and also lane 2 lane 3. Remaining area is in remaining area and click OK. Close this. So we have defined all the stage information, the moving load analysis information, and now we will define some analysis parameters. So to decrease the time required for the analysis, we will just analyze the live loads for a few elements. So I'll just select one of the mid-span elements, which is this one, for example, element 174. This I will include in a result group, so I'll just right click on structure group, new, and say result group and drag and drop this group here so that this includes the element. And now I'll go to analysis, moving load, and include only that element in the calculation, so I'm not checking for any reaction, any displacement. I'll check for that particular result group, a set of elements. If you want to check for all the elements at once, you can check on all the calculations, but yes, the analysis time required will be more in that case. Click OK and switch back to the activate all mode. If I click here, activate all, and now select construction stage, check on the construction stage parameters and click OK, and now run the analysis. So analysis, perform analysis. The message window keeps telling you from time to time what step are you in the current analysis. So the analysis is done. Okay, I'll just check off all the boundaries so that it's a bit clear on display. Okay, now see the results. So the results, we can create some load combinations. So results, load combinations. So if we want to do steel design, we create a combination under steel design. Select steel design here, auto generate, select Eurocode and click on the road traffic. We can select which is characteristic combination. Frequent is load model 1, click OK, and automatically the load combinations as per Eurocode are generated by the software. Then select concrete for the pile design, so auto generate, again Eurocode, frequent value, click OK. Okay, so same thing for the concrete, load combinations are generated. Okay, now I'll close this. And now we'll see the results. So for the results, we go to first reactions, select a particular case or combination, say self weight, and check on values, apply. That gives you the reaction for each and every support. Okay. You can also get a tabular result if you go to result tables, reaction, and select a particular load case, click OK, and you get the results at each and every support node. Okay. Next thing is the stage-wise deformations, or we can say the final stage deformation. Post CS is the results after the construction. So this is the deformation for self weight. I'll check on hidden view, check on displacement contour from here, TZ vertical deformation, deform, and check on legend and apply. So that gives you the deformation of the bridge. This is in meters. We can change the deformation to mm. That is the deformation under self weight. We can also change the system of display from exponential to fixed. Let's make it fixed here. So that's the minus 12 mm in the downward direction. That's the deformation of the bridge. Now what will be interesting is to see the stresses for and the forces for the composite section. So we will examine the forces stage by stage. So go to stage 1 and check on beam diagrams. We have so many different load cases generated based on the type of result you want. So summation is the summation of all creep, shrinkage, dead loads, erection loads, pre-stressing loads if any. So that's the summation of all these forces. We'll check CS summation, check the bending moment diagram. So click on solid fill and apply. So that is the bending moment diagram in the piles. I'll check off deformed shapes so that it's more clear from here. Okay, the units are in kilonewton meters. Now we go to the stage 2. The stage 2 shows the bending moment diagram for the steel girders. To focus more on the steel girders, we can just select the steel girders, check off hidden, select only the steel girders and press active. So that's the steel girder deformations bending moment. Now for each composite section we have two part wise results. Part 1 means steel or first part of composite section. Part 2 is the concrete deck. So if I select part 1, it will give me the same result for stage 2. Part 2 result will be 0 because there is no concrete poured in this stage. Stage 3, this is the stage. I select total, gives me the bending moment diagram for part 1, part 2. If I select so stage 3, stage 4 where concrete has been activated in stage 4 gives some bending moment in part 2. Part 1, which is steel, gives some value of bending moment, and then total part 1 and part 2 gives this bending moment diagram. Similarly for stresses, for the final stage we can check what is the stress. You can check the stresses at different fiber location for concrete and steel. So if I want the stress at the bottom flange of steel, I select part 1, which is steel from here, and select the bottom fiber, which is from the diagram I can see it's 0.4 or 0.3. Select 0.4 and select apply. So that's the stress diagram. You can see it's approximately 250 MPa at the bottom flange of steel. You can also see the stresses in the concrete. So for that we select part 2 and select top or bottom of concrete, say top of concrete 0.1 and apply. So this is the stress in the top of concrete, which is approximately -3 MPa, maximum stress, minus as in compression. So I'll close this, and now we will see the moving load results. So for generating the worst case vehicle position, we have the moving load tracer option. So results, go to post CS and go to moving load tracer and beam forces. And if you remember, we did the analysis for only one element, 174. We can just also click on the element directly from here. Okay. that's this element, and beam forces, and apply. That gives us the position of the load model 1 vehicle and what is the bending moment diagram, bending moment value for that vehicle position. These are the tandem loads and the UDL, and then we'll see the position causing the worst bending moment at this particular element for load model 1 and load model 3. So select this option and click apply. That gives us the position of the worst case position of the vehicle for the combination load model 1 and 3. We'll see from the top view. So if you see here, it follows the code based spacing between load model 1 and 3. That's the load model 1 vehicle over here. There's a 5 meter spacing, and then you have the load model 3 special vehicle SV196. On the other lane we have load model 1 axle, load model 1 axle here, and the remaining area has been loaded with UDL. And you have the maximum value of the bending moment for this load position. We can convert this position of loads into a static load by just clicking on this option of write min max to load file. So if I say load model 1 vehicle, I want to change this into a static load so that I don't have to run the live load analysis again. I can run it as a static load case itself. So I click on write min max load, click OK, and just copy the entire thing. So Control A and Control C, and go to Tools, MCT command shell, and paste here Control V and run. So it will ask you to delete the results. I click yes, delete the results. Now if I don't want to run the live load analysis again, I can just right click here, moving load analysis, and check off force. So live load analysis will not be run for any calculation, reactions, displacement of forces. Click OK, and if you see in the works tree, you will have a new load case with the exact vehicle position converted in the form of element loads or point loads on the bridge, on the deck. And if you run the analysis for this load case, you will have all possible concurrent or coexisting force results, reaction results, displacement results for this vehicle position. Now for the design purpose, as I said earlier, we need a special material for main girders, that is the SRC material. So we go to groups again, double click on main girders, go to works, and drag and drop SRC. So SRC has been assigned here, and now we rerun the analysis. So analysis is completed now, and we will now see the design procedure. So go to design, and first we will start by designing the composite steel girders. We will design the mid-span girders for this example. So first we select design, go to composite design, Eurocode 4, select design parameters. So we enter some partial factors here. We enter some partial factors as per the code here. So for example, for concrete we enter 1.5, For reinforcing steel 1.15, structural steel gamma m0 as 1, m1 as 1.1. For the shear studs 1.25, and for fatigue strength we enter 1.1 and 1.1. For gamma mf and gamma mfs, design life of the bridge would take us 100 years, and we'll check for all these checks. So check them all and click OK. Now we'll enter some rebars for the midspan. So for the rebar material, we select design material, select here, and keep reinforcement material as Eurocode class B. Say modify, close, and then we enter the rebars in the longitudinal reinforcement dialog box. Longitudinal reinforcement, select midspan and define a guideline. So that will be 0.05, that is 50 mm cover, and input method B, select first point here, second point over here on the guideline, and enter the number of rebars, say 20, with edge rebar, and the diameter is P25 or 25 mm. Add, repeat the same procedure for the bottom rebars here. Add and apply. So that's the rebar is added on the midspan. Close this. Now we will define some longitudinal stiffener for the plate girders. So longitudinal stiffener, select midspan, width of the stiffener, which is say 0.5 meter, thickness 0.05, number of stiffeners say 1. So now the position of the stiffener from the top of the girder, say it's 0.8 meters from the top. Spacing of the stiffener, you give some spacing value which is 1 meter and replace. So that's the spacing is added, the longitudinal stiffener information is added here. Close. Now we enter the information for the output design position. So this is where we specify which element has to be designed. So select design position, and just I'll change it to the top view and say I want to extract the result for these midspan girders, and both I and J location apply. And the next is position for design output. Now the software generates an Excel sheet containing all the step-by-step calculations. So for one of the elements we'll be generating that Excel sheet. So I'll just write down the element number to select it. So 174, enter, and that element gets selected. Click apply and close. Now for that particular element there, we'll define some shear connector information. So select element 174, enter, and we'll start by entering number of connectors per girder. So 3, tensile strength is 4, tensile strength or FU of the shear connectors, that is 600,000 kPa. Diameter of shear connector is 20 mm. Overall height, that's 100 mm. Center to center spacing, that is the transfer spacing, and that is 80 mm 08, and spacing longitudinally, that is 1 meter, and apply. Then repeat the same for the same element. We will add some transverse stiffener, so we select that particular element 174 and we'll add the stiffener information for the transverse direction stiffener. So this will be used for the shear buckling resistance for the web. So height of the stiffener, that is 0.7 meters. Thickness of the stiffener, that is 0.02, 20 mm, and distance between the stiffener, two stiffeners, that is 2 meters, and will not give any intermediate rigid or intermediate flexible stiffener, so just click apply, and then we'll add some type of load application data. So what type of load application is it as per the Eurocode, type A, type B, or type C? So we'll select again the same element. We are selecting this element because we just want to extract the result designed for one particular element. We have to do the same procedure for all the elements, so in that case we select all the elements at once. So I'll just enter 2 meters here, 5 and 6.5, and finally some damage equivalence factors for the fatigue analysis. So we'll enter some values here, 0.6 and 1.2 for example. I can select that element and apply. Then some serviceability, the load combination type, so which is quasi-permanent and which is frequent. So S will select the serviceability load combination from the steel design types. So let's say SLCB 11, that's quasi-permanent, 12 is frequent, 13 is characteristic. Click OK, and then we click on design. So that's designed all the elements which we selected in the mid span, and we can see the results from the design result tables. So bending resistance, click OK. So we selected few elements only for the design check. Now it's showing the negative and positive moment checks. MPLRD, which is plastic moment of resistance, elastic moment of resistance, and what is the moment of resistance here. The class of the section, top flange class, bottom flange class, web class, and the final section class. Also we can see the result table for vertical shear resistance, that's the plastic shear resistance, VBRD, the shear resistance. Anything that is not passing will be marked in red, and we can also print out the result in the form of Excel sheet. So if I click on print result, create a new file, save as, say, design report, click save. So click yes here, and this will create an Excel sheet of calculations containing all the material information, section information, bending resistance check, classification of the section. So all the parameters that you entered will be considered for the design check and the report generation for the steel composite steel girders. Now we will do the design for the piles. So for the piles, we go to the reinforced concrete design, go to design code, we select Eurocode 2, and partial safety factors can be entered as per the code. We can modify the concrete material for the design. We can use some other material also. Now we can define some reinforcement for checking the piles. So I'll use the column section data for checking, and some spirals or ties. So say 12 mm dia ties, spacing 3, and number of reinforcement rebars in the section, so 20, size 25 mm dia, still also 25 mm dia, and the clear cover is 0.1 meters, and replace. So that's the pile, the drawing showing the rebar arrangement. Cancel. And now go to RC design, concrete code check, column checking. So that will check all the pile sections. Okay, that's design is complete, check is complete, and it shows some red marks here, which means the section is failing. We can click on the pile section and see the graphic report to see which checks are failing. So it shows that the pile is failing under axial load capacity check, moment capacity check, the shear force is okay. We can also extract a detailed result. So just click on member, select any particular element, and we can either see PM interaction diagram, or we can also click on detail, gives us a detailed report, step-by-step calculation for the reinforced concrete design check. And we can also design the steel cross beams. So if I just double click on cross bracing and click activate, so we have the steel cross bracings here. We can select steel design, steel code check, and that will design the steel members. You can select them, click on graphic, it will show us a check for the steel section. Blue means it's okay. Also, if you click on detail, you get a detailed report of all your steel sections. What is interesting to see is that you can even optimize your sections. So if the combined ratio here is 0.845, you can go for a more economical section by clicking on change and select the code from where you want to select a particular section, say BS code, and channel type of section, search satisfied section. So you can say 0.9 to 0.21, search for a satisfied section, or since there is no other economical section satisfying this section, you can even go for an I section and say search satisfied section. It gives us a list of several I sections which can satisfy this check, and also give you a more utilization ratio from 0.9 to 1. So you can select one of them and say change in close. So design will be rechecked, and after rechecking it says it's failing, so you can again change it back to some other section. So it's almost 1 here, and so this way you can ask the software to automatically change a particular section based upon the ratio of your utilization. Okay, so this one fits here and the section is passing. Okay, so after the design you can also create a detailed report for your presentation purpose. So what you can do is, I'll activate everything here now, and say you want to save this image. You can also display in different colors. So if I click on this box, go to display option, draw, and change it to material color. So say apply, so random color, apply. So this shows in different colors the different sections or materials. Click OK, and now if I take a snapshot of this, right click, dynamic report image, and save it as isometric view. You can save the plan also, right click, dynamic report image, plan view. Also I can take some snapshots of the results, so I can go to results and say deformations, displacements, and for a particular combination, say CBS SLCB14, so something like this, and right click and take a snapshot of this, say displacement. Okay. I can also go to result tables, go to reactions, and say display the reactions for the self weight. So right click here, save this table as a reaction table. I can also ignore all the moments for the reaction generation, focus only on the horizontal and vertical reactions. So click OK, and then I can create the report. So if I go to tools, dynamic report generator, click new document. You can also open an older document with your own template. Click OK, and a Word file will open up. Go to report tab of the tree menu, and you can write down some text here, design report for example, and start drag and drop all your images which you saved. So drag and drop, isometric view, and isometric view gets saved here. You can drag and drop plan gets saved, drag and drop displacement gets entered here. You can also drag and drop your tables, reactions, so all the reactions get entered. Also what you can do is drag and drop your section summaries. So if I want to include the summary for my composite steel section, I can go to section summary, midspan say, and drag and drop, and you can see here that the composite section information has been entered, the dimension, the section properties for before composite and after composite section. You can also copy some text in your report. So you can copy in your static load cases. You can also copy your bill of materials, weight, volume and area of all the members. You can also copy in your load combinations. So all these things you can enter in your report, and you can, once you define your report and you go and change your model slightly, you don't have to come back and edit anything. You have an auto generate button which will regenerate all the report images and tables automatically for you. So for example, if I go back and if I say change the dimension of my main girder, say if I make it, right click here, go to properties, and if I make the dimension as 2 meters for instance, so everything is deleted. I'll reanalyze, so it looks a bit funny here, the shape. So once the analysis is done, results are recalculated, and now I can just click on the dynamic report regeneration button and say check on everything, select all tables and everything. I can just click select and I can say regenerate, so it will regenerate the Word file which I just created and modify everything, all the images, all the results, all these sections. So you see the image has been modified here. Also your displacement, these are contours, your reactions, they are all modified now. The section has also changed to a 2 meter deep web. So that summarizes the section properties and the material properties, the modeling procedure, the load combinations, boundaries, results, construction stages, live load optimization, and also the design for the composite steel girders. If you have any questions, please write to uksupport@midasuser.com. I hope you enjoyed this video. Stay tuned for more videos. Thank you.